Hello dear students, my name is Venkatesh. In the last session we discussed that types of chemical reactions and in that average rate of reaction is completed. So now after the average rate of reaction, one more rate of reaction, that is instantaneous rate of reaction. So what is the meaning of instantaneous rate of reaction and how can you identify that instantaneous rate of reaction? And how can you express the instantaneous rate of reaction? We will discuss it. So simple example I will say that instant nothing but water, within the small time we can prepare that. Same here also, instant nothing but within the small time. Rate of reaction nothing but what? Change in the concentration of the reactant or change in the concentration of the product with respect to time. That is called what? Rate of reaction. So if you take any chemical reaction, in that the concentration of the reactant always it is decreases and the concentration of the product always it is what happening? Increases. Now rate of reaction nothing but here decreasing the concentration of the reactant or increasing in the concentration of the product with respect to time is called as a rate of reaction. Now instantaneous rate of reaction nothing but what? The rate of reaction it is possible at the small intervals of time is called as a instantaneous rate of reaction. So now how can you define the instantaneous rate of reaction here? Change in the concentration of the product or change in the concentration of the reactant at the small intervals of time is called as a instantaneous rate of reaction. So we can say that what? Decreasing the or increasing the. So we can say anyway, change in the concentration of the reactant or product within a small intervals of time is called as the instantaneous rate of reaction. So small intervals of time nothing but the small interval of time we are showing the symbol with dt. dt nothing but what? Small time change in the time very small. So now at this time we are showing the rate of reaction is dx by dt. We can express the rate of reaction at the instant time. How can you express here? Dx by dt. Change in the concentration of the reactant by time. Small change in the concentration or small change in the concentration of the reaction by what? Further time is taken. Now this is a dx by dt, right? So now we are expressing the what? Dt, that means the small intervals of time. Dx by dt nothing but at that small intervals of time we are expressing the what? Rate of reaction. Now in differential calculation, where in differential calculation, okay, in differential calculation delta t, in differential calculation delta t nothing but what? Again change in the time, but it is not a instant change in the time. Simply showing the symbol with delta t. Instant time nothing but showing the symbol with what? dt. So in differential calculation when delta t becomes very small, okay, in differential calculation when delta t becomes a small value, otherwise it is approaches to 0. Otherwise it is approaches to what? 0. It is approaches to 0. What value approaches to 0? Delta t either becomes the very less value and approaches to 0. The ratio between the delta, this is what? This is delta a. The ratio between the delta a by delta t. The ratio between the delta a by delta t maybe we are represented by the derivative of dA by dt. We can represent it by the derivative of what? dA by dt. That means when the change in the concentration, delta A nothing but what? Change in the concentration very less or approaches to 0. That means at the very less time the concentration of the reactant or concentration of the product will be changed very small. Okay, so the small change if it is possible in a chemical reaction at that time we can show the symbol with the dA by dt. That is only what? Instantaneous rate of reaction. Instant nothing but what? Very small time. Very small time, how much concentration will be changed? Very small concentration will be changed. So that very small concentration, that means that delta A change in the concentration when very small or approaches to 0 at that time we can show that dA by dt. You can show that is what? dA by dt. So now we can write rate of the reaction at instant rate of the reaction. Instant rate of reaction is equal to minus dA by dt when you are taking the reactant is equal to minus dA by dt. We can represent minus delta A by delta t, otherwise equal to minus dA by dt we can represent. So for example, I am taking one chemical reaction, that is reactants are converted to product. For example, I am taking that what reaction, reactant are converted to what here product. At the time, rate of instant, otherwise instant rate, how can you represent? Instant rate is equal to minus dr by dt is equal to plus dp by dt. That means what here? Decreasing the concentration of the reactant, always you show the symbol with minus. By what? Particular time it is taking. Next, what is here? Plus dp by dt. Plus dp by dt, nothing but what here? Increasing in the concentration of the product, you show the symbol with plus and dt. So now at the instant time, we can represent the rate of reaction in terms of d. In terms of what? D. So remaining is as usual same. So in the decreasing the concentration of the reactant per time and decreasing the concentration of reactant by time and increasing the concentration of product by time. So this is what instantaneous rate of reaction. Instantaneous rate of reaction. So next we will discuss that calculation of instantaneous rate of reaction. Let us see what is that calculation of the instantaneous rate of reaction. So let us see that how can you calculate the instantaneous rate of reaction. Calculation of instantaneous rate of reaction. Let us see that calculation of instantaneous rate of reaction. Calculation of instantaneous rate of reaction. So let us see that how can we calculate the instantaneous rate of reaction. To calculate that, I am taking one graph. The graph I am taking here, this is the graph. I am drawing the graph between the concentration of the reactant and the time. So for what I am drawing the graph here, concentration of the reactants and what here, time. Now we know that when the time is increases, the concentration of the reactant always decreases. And finally, we will get the graph. Such type of graph we will get, okay, when the concentration of the reactant and time, when you draw the graph, always you will get such type of graph, because when the time is increases, always the concentration of the reactant what happening here decreases, right? So let us see that here I am taking that at the instant time. At the instant time, we want to find the rate of reaction. So instant time nothing but, for example, this is the I am taking as a t1 time, and for example this is I am taking as a t2 time. But I want what? Instant time. We can find with the help of these t1 and t2 average time we can find, that we discussed already. Now we want what? Instant time. Instant time nothing but at any one of the time, otherwise at the small interval of time. So I am taking the small intervals of time, this I am taking. So at this particular point, I want to find the instantaneous rate of reaction. Okay, so now for this I am drawing one tangent. So okay, what I am drawing? I am drawing one tangent. Now this is the one tangent line, and in this tangent, on this slope, when I am drawing the tangent, and this curve, particularly at this point, this curve, it is indicating the rate of instant reaction or instant rate of reaction. Instant rate. Okay, in this curve, when I am drawing the tangent here, on this point, whatever the curve we are obtaining, that curve is indicating the instant rate. So now with the help of this one, we can identify the instant rate of reaction. So whatever the graph we are getting at this t point, this is the graph we are getting. This curve, small curve we are getting. So that is the what? Instant rate. That is what? Instant rate. So this is the what? Instantaneous rate of reaction. Right. So the next one is reaction lifetime. So what is the mean of reaction lifetime, and why we are using the reaction lifetime? So generally the reaction lifetime we are using to determine the various reactions. To determine the various reactions, we are using the reaction lifetime. So what is the mean of lifetime? So generally lifetime nothing but here the time taking to complete the 98% of the reaction. The time required to complete the 98% of the reaction, or time taking to proceed the 98% of the reaction, is called as a lifetime of that reaction. So how can you say that lifetime? It is defined as the time taken by any reaction. It is defined as what? Time taken by a reaction to proceed 98% completion. Time taken by a reaction. So what I am doing here? Time taken by a reaction to proceed. Time taken by a reaction to proceed 98% completion. To proceed 98% completion is called as a lifetime of the reaction. What we call here? Lifetime of the reaction. Now the lifetime of the reaction, if it is less, that means the reaction will be complete within the less time. So lifetime of the reaction, if it is less, the reaction will be fast. Lifetime of the reaction, lifetime of the reaction, if it is lesser, that means the reaction we can say is very fast. So now this lifetime we are using to identify the various types of reactions. That means the reaction is very fast, other reaction is very slow, other reaction is average. Based on the what lifetime we can understand. Lifetime of the reaction is less, the reaction will be fast. Lifetime of the reaction is more, the reaction will be slow. Lifetime nothing but what? To complete the reaction, the time is taking. For completing a reaction, generally 1 week of time it is taking. We can say that is the what the reaction is very slow. And to complete the reaction is taking within fraction of seconds, the time is taken to complete the reaction, we can say there is a very fast reaction. So based on the lifetime of the reaction, we can say that the reaction is very fast or the reaction is very slow. So not only reaction lifetime, we have the off lifetime also. What we have? We have that off lifetime also. So what is the meaning of off lifetime? Reaction lifetime nothing but the time required to proceed the 98% completion of the reaction, otherwise time taken to complete the reaction we call as a lifetime. Half lifetime nothing but what? The time required to complete the half amount of the reaction. The time required to complete the half amount of the reaction is called as a half lifetime. To complete the half amount of the reaction, how much time is taking, simply that is called as a half lifetime. And we are showing the symbol with a T off. I shown the symbol with what? T off. Same here also, half lifetime of the reaction, if it is less, that means the reaction is very fast. That means the reaction is what here? Very fast. So this is what lifetime of the reaction and half lifetime of the reaction. And half lifetime you shown the symbol with what? T off. Right. So the next one is a calculation of the rate of reactions. How can you calculate the rate of reaction? Let us discuss here. So to calculate the rate of reaction, I am taking a general reaction, I am taking, that is 1 mole of A converted to 1 mole of B. 1 mole of A converted to what? 1 mole of B at the time T equal to 0. At the 0 time, the concentration of the reactant I am taking as A naught. At the 0 time, the product formation does not form. So I am taking the product formation is what? Concentration 0. Next, after some time, that means at T equal to T time, the concentration of the reactant is AT and the concentration of the product I am taking as a BT. That means some amount of the concentration is converted from reactant to product. Right? So now here, how much amount of concentration converted? For example, X amount of the concentration from reactant to product it is converting. From how much? From the A naught, X amount of the concentration is converted to product. That means AT nothing but can I write as a naught minus X, because from that A naught, X amount of the reactant converted to product. That means AT means what? A naught minus X. How much amount of concentration converted product? BT. So BT nothing but here what? This is X, because X amount converted to product. That's. Now here, for this reaction, now I am representing the rate of reaction. Rate of reaction nothing but what? Decreasing the concentration of the reactant and increasing the concentration of the product. So now I am writing here what? Rate of disappearance of A. What I am writing here? Rate of disappearance of A. Rate of what? Disappearance of A. Rate of disappearance of A, because in the chemical reaction always the concentration of the reactant is disappearing. So that's why rate of disappearance of A. So how can you show that rate of disappearance of A here, right? So let us discuss that rate of disappearance of A. Generally we are showing the symbol with disappearance nothing but we are showing the symbol with minus delta A by delta T. We are showing this with symbol. And I discussed that previous minus nothing but we are showing the symbol that is indicating the concentration of the reactant is decreasing. So actually why you are writing the minus, let me discuss here. Okay. So now here, rate of disappearance of A, that is delta A by delta T. Why I am writing the minus, I will say here, delta A by delta T. Delta A nothing but what? Change in the concentration of the reactant. Change in the concentration means from where to where? From the final time minus initial time. Okay. Now what is the concentration of the reactant at final time? AT minus A naught. By time at the final time is what? T minus initial time is what? 0. Now AT nothing but what can write? A naught minus X. So A naught minus X. Again minus what is there? A naught by T minus 0 nothing but T. So this is plus A naught, this is minus A naught, both will be cancelled. So finally what we will get here? Minus X by T. What will get here? Minus x by t. So what is that minus x by t indicating? Delta A by delta t. Delta A by delta t nothing but what? This is the rate. This is what? Rate of the reaction. So rate in terms of what? Reactant. So here rate of the what? Disappearance of A is what? Minus x by t. Minus x by t nothing but that is the rate. But rate always is positive. Never the rate is not negative. For example, I am going on a bike. The speed, rate nothing but what? Simply speed. Okay. The time we are taking to move some area to other area. Same here also, speed nothing but what? Speed always it is either 20 kilometers, either 30 kilometers, either 40, 50, 60, 70, 80 we are taking. But otherwise finally it is 0. But rate or speed cannot be negative. We can't observe the speed minus 10, minus 30 kilometers, minus 50 kilometers. That means rate cannot be negative or speed cannot be negative. But here, according to the reaction, rate of disappearance of A, what you are getting? Minus x by t. But rate never it is a negative. So, to make the rate is a positive, we have to multiply with the negative. You have to multiply with what? Negative. So, that's why always when you are writing the rate of reaction, minus we are writing in the what rate of disappearance of the reactant. Why are writing the minus? Because in the disappearance of the reactants we are getting the minus value, but minus nothing but it is the speed does not minus. So that's why you have to multiply with again minus. So this is the reason why always we are writing the concentration of the reactant here minus. That means that is the reason here. So next rate of disappearance of A completed, that what you got? Minus x by t. Again we are multiplied by the minus x by t. Next rate of appearance of A. Rate of what? Appearance of A. Rate of appearance of B, because B is forming. Okay. So how can you show that? Delta B by delta T. What is that? Delta B by delta T here. Okay. Rate of what? Appearance of delta B by delta T. Delta B nothing but what here? That final concentration. What is that here? BT. BT nothing but what? X. And the initial concentration is what? 0 by T minus 0. X minus 0 by T minus 0. Finally, what will get here? X by T. Finally, what will get here? X by T. So, rate of appearance of B, X by T. Rate of disappearance of A also what you got? X by T. So, that means the rate of reaction, the change in the concentration of the reactant and the change in the concentration of the product will be equal. Otherwise, disappearance of the concentration of the reactant or appearance of the concentration of the product, both will be equal. So, this is what calculation of the rate of reaction when you are taking the number of moles of the reactant is 1 and the number of moles of the product also 1. So, let us see that one more example, concentration of the reactant when I am taking the 2 moles of A and 2 moles of B. How can you identify here? When I am taking what? 2 moles of A and 3 moles of B I am taking. For example, what I am taking? 2 moles of A and 3 moles of B. 2 moles of A I am taking and 3 moles of B. Now let us see that at the t equal to 0 time, the concentration of the reactant is A0 and the product formation is 0. Next, at the time t equal to t, the concentration of the reactant is AT and the concentration of the product is BT. AT nothing but what? Some amount of the concentration is converted to product from the A0. So now A0 minus how much amount of concentration converted? 2 moles we are taking, right? So 2x is converted to product. How much amount of product is forming? So from here how much is converting? 2x. But how many moles is there here? 3 moles. So the product formation is what here? 3x. Now let us see that rate of disappearance of A and rate of appearance of B. So first one here what? Rate of disappearance of A. Let us see that rate of disappearance of A. So how can I write here? Delta A by delta T. Delta A by delta T. So delta A nothing but what? Change in the concentration of the reactant, final time minus initial time. Final time nothing but what? That is A and T. Initial time nothing but A0. The time is what? T minus 0. Now let next to discuss AT nothing but what? A0 minus 2x. A0 minus 2x. And the initial time A0 nothing but what? Again it is A0 by what? T. So again here A0 and A0 will be cancelled. Finally what you get? Minus 2x by T. What you got here? Minus 2x by T is equal to minus 2x by T. So again the rate is what? Negative. But rate can't be negative. Always it is what? Positive. So that's why again you have to multiply with the negative to make the positive. This is what rate of disappearance of A. So next what? Rate of appearance of B. Rate of appearance of what? B. So how can you say the rate of appearance of B? Delta B by delta T. Delta B nothing but what? Final concentration. What is that? 3x. And initial concentration is what? 0. So finally 3x minus 0 by T. So finally what you got here? 3x by T. But before that, when you are taking the 1 mole of the reactant and 1 mole of the product, we can understand that the decrease in the concentration of the product and increase in the concentration, decrease in the concentration of the reactant, increase in the concentration of the product, both will be same. X by T we got. But it is not possible here. Let us see here. Rate of disappearance of A is what? 2x by T. Rate of appearance of B is what? 3x by T. But it is not equal. But in a chemical reaction or in the rate of reaction, the change in the concentration of the reactant, change in the concentration of the product will be equal. But here if you see that it is not equal. To make that equal, we have to do some process. So let us see what is that process. So in the rate of reaction, the concentration of the, okay, here what? The rate of disappearance of the reactant is what? 2x by T. 2x by T, because already we multiplied with negative, no problem. Now rate of the appearance of B is what? 3x by T. Actually both will be equal, but it is not equal. Okay, so now to make equal, what you have to do here? To make that equal, what I am doing, this 2x by T, that means disappearance of the A, I am multiplying with 1 by 2, and this appearance of the B, I am multiplying with 1 by 3. When I am multiplying here, what I will get? This 2 will be cancelled and this 3 will be cancelled. Finally, rate of appearance of A, x by T, rate of disappearance of A, x by T, and the rate of appearance of B also what I am getting? X by T. Now how it is getting? Now we are multiplying with 1 by 2 and you are multiplying with what? 1 by 3. Always in the chemical reaction, the rate of reaction, the concentration of the product and concentration of the reactant will be equal. Not concentration, change in the concentration. Change in the concentration of the reactant, change in the concentration of the product will be equal. But here if you see that according to reaction is not possible. But we have to make the equal. For that we are multiplying with some suitable numbers. Now, if you see that any one of the chemical reaction, when it is having the coefficients, when it is having the coefficient 2 or when it is having the coefficient 3, okay, we have to do that 1 by that coefficient particular. 2 is there, what you are doing? 1 by 2, we are multiplying with 1 by 2. 3 is there, what you are doing? The rate of reaction multiplying with 1 by 3. Whatever the coefficients we are taking in the chemical reaction, that coefficients we have to multiply with that reaction, as in the form of what? 1 by 2, 2x by T. Here what? 1 by 3, 3x by 3. So any chemical reaction you take, the coefficients are, we are multiplying with in the form of 1 by that x number of coefficients. So this is the what? Calculation of the rate of reaction. By using this method, we can do the so many questions, we can do that, otherwise so many examples we can do by using the calculation of the reaction. So this is the topic, and next session we will discuss about the order of the reaction, 0 order, first order, second order we will discuss, and the next we will discuss that related problems also.